sunlight, wind power, and geothermal energy. We can use these sources of renewable energy without imposing a burden on the global environment. Today, in Japan and around the world, deployment of renewable energy is moving forward. The National Institute of Advanced Industrial Science and Technology, or AIST, conducts proactive research to advance the use of renewable energy. Under government policy, AIST launched a new research organization in April 2014. Its goal is to make Fukushima the prefecture that pioneers the intensive introduction of renewable energy. That new organization is the Fukushima Renewable Energy Institute, or FREA. Let's start by looking at the Institute's facilities. This is the main building. Many ingenious design features give the building outstanding environmental performance. This is where ordinary experiments and administrative work take place. To the west of the main building is the experiment building. Large floors offer an open floor plan that allows for flexible arrangement of the latest equipment. There is even a room for a line dedicated to manufacturing silicon solar cell modules. To the north of the main building is the demonstration field. Photovoltaic power systems have a rated output of 500 kilowatts. Here, a number of different manufacturers' panels are laid out. Wind power generation systems have a rated output of 300 kilowatts. This is where research into and development of the newest wind turbine technology takes place. To the west of the demonstration field are the Energy Control Building and experimental facilities. Here, research is conducted into storing and managing power generated by photovoltaic and wind power systems. This is where researchers, ranging from those in the local community to those from universities, gather to conduct research into renewable energy. Now let's take a look at the 6 areas of research currently underway. These are the next-generation silicon solar cell development facilities. The entire process of developing crystalline silicon solar cells can be handled here, from the slicing of silicon ingots to the production of modules. This is the first public research institution in Japan to have a line of this class. The photovoltaic power team makes full use of this equipment to develop thin crystalline silicon solar cells of under 0.1 millimeters in thickness and the solar modules that use them. Thinner wafers make it possible to hold down the cost of manufacturing. Many companies have already come together for this project. Research on and the development of processing technology that will lead directly to mass production is now underway. This is a double-glass silicon module, one of the fruits of that research. These inexpensive, light, highly efficient, and reliable modules will soon find their way from this facility to users around the world. This is a seismic sensor that picks up very weak seismic signals in a borehole. The geothermal energy team makes full use of this kind of instrumentation to identify and monitor geothermal resources lying many kilometers beneath the ground surface. Under Japan lie what are estimated to be the world's third largest reserves of geothermal resources. If technology can be developed to inject liquids into highly heated rock, extracting steam, and if geothermal power plants were to be established throughout Japan, the nation would have a huge amount of power from geothermal energy. However, because of numerous problems, various uncertainties, cost, the need to coexist with hot spring owners during conventional development, geothermal energy has yet to see widespread use. By analyzing data from a wide range of instrumentation, the research team is working to develop technologies that will enable us to identify geothermal resources and their quantities. The team is also developing software for simulating a variety of geothermal development processes. Research and development continue towards the day that geothermal power generation becomes the trump card in the use of renewable energy. This is the heat exchanger for the ground source heat pump system, or the GSHP system, installed by the Institute for conducting experiments. It extends 40 meters below the surface. The GSHP system works like this. The subsurface temperature remains almost constant throughout the year. Thus, the subsurface temperature is lower than the atmospheric temperature in summer and higher in winter. By exchanging heat between the subsurface layer and the ground surface, the heat pump can help air conditioners run more efficiently. Snow melting systems can also be operated more efficiently in the winter to melt the snow that accumulates on roads. The shallow geothermal and hydrogeology team studies groundwater flow and geological conditions in an attempt to scientifically demonstrate the suitability of ground source heat pump installation in a particular region. Currently, work is underway to prepare a map of potential installation locations for the GSHP system in the Tohoku region, primarily in Fukushima Prefecture. If the system can be designed based on this data, the ground source heat can be used effectively in this area. The ever-changing wind. Improving the efficiency of wind power will require wind turbines that can accurately read and respond flexibly to changes in wind speed and turbulence. The wind power team mounts devices called LiDAR on wind turbines in an effort to develop technology for accurately reading the wind. LiDAR emits infrared laser light from the forward portion of the wind turbine. This is then used to measure the round-trip time of the laser, which is bounced off of aerosol particles in the air and changes in wavelength. The round-trip time tells us the distance of the aerosols, while changes in wavelength tell us wind speed, taking into account the Doppler effect. From these results, one can control the angle of the wind turbine blades and nacelle. This technology is expected to improve wind turbine power generating capacity by 5% and extend system lifetime by 10%. This is the beamforming-based noise source measurement system. It uses a total of 30 microphones to determine where on the turbine blades noise is coming from. Equipment installed around the wind turbine is also used to measure acoustic power emitted by the wind turbine. Data like this can be used to accurately analyze noise from the wind power generation system and enhance assessment precision. The amount of power generated by photovoltaic and wind power systems can vary greatly with the weather. Storing power during times of peak generation is highly convenient. This is a unified demonstration system of hydrogen energy carrier production and utilization. The amount of power used per day by about 1,000 typical households can be stored in the form of a hydrogen energy carrier. This is the world's first such system. With this system, renewable energy is used to obtain hydrogen through the electrolysis of water. The hydrogen is combined with toluene to form methylcyclohexane, or MCH, which is then stored and transported. Substances such as MCH are referred to as hydrogen energy carriers. When power is needed, the hydrogen is removed from the MCH and mixed with diesel oil for power generation using a cogeneration engine. The key to this system will be the R&D of the hydrogen carrier, a catalyst for adding and removing the hydrogen, and the cogeneration engine. The hydrogen energy carrier team is conducting research into all of this. In this laboratory, they are running a diesel engine on two kinds of fuel, hydrogen and diesel oil, and extracting power and heat. The question is how to provide society with a stable supply of renewable energy. The challenges for the research team continue. Efficient use of renewable energy requires selecting equipment that is suited to each region's climate and energy demand. The Energy Network team conducts research into solar cells, power conversion equipment, and power storage systems. It is also necessary to understand how energy is consumed in each region, managing power according to the power sources and heat sources available to its users. Based on demonstration data, the research team is working to establish the best mix for providing energy. For example, this is FREA's energy network. Power generation is available to the Institute via solar cells and wind turbines, with any surplus electricity generated sold to the power company or stored in batteries or as hydrogen. Conversely, if we are short on power, we use our stored energy or purchase it from the power company. This requires flexible power management that takes into account a span of about a week at a time. Aiming to arrive at the ultimate mix of energy, we conduct demonstrations and simulations using a range of renewable energy technologies. FREA is actively promoting collaboration among industry, academia, and the government. One example is the program for promoting technologies invented by industry in disaster areas in Tohoku. FREA provides free technical support to companies working to commercialize renewable energy-related technology in Fukushima, Miyagi, and Iwate prefectures. To date, we have rolled out numerous projects. We have also begun a program aimed at nurturing young students through joint research between local universities, national colleges of technology, and FREA. FREA also enters partnership agreements with research institutions outside of Japan. Results gained from such joint research will be shared with the rest of the world. Reconstruction of disaster-affected regions. Matching renewable energy use with local climates and communities. Developing the next generation of young scientists. And maintaining both a community-based and international point of view. Together with its partners in the community, FREA will invigorate society and increase the use of renewable energy.